Hello, this is Jack Jackson. In this video, we're going to look at the Central Limit Theorem applications. So we're going to look at several real-world problems here that make use of the Central Limit Theorem and sampling distributions. So here's the application 1. According to USA Today from July in 2009, the mean amount spent on a wedding dress is $1,032. Suppose this is accurate and the cost of a wedding dress is normally distributed with standard deviation $550. A sample of the cost of 20 randomly selected bride's dresses is obtained. If multiple such samples were made, completely describe the distribution of the mean cost of such samples. And then what is the probability that the mean cost of wedding gowns is between $800 and $1,200. See if you can go ahead and work this out based on what we've learned already. And when you come back, then you will check your answer. So press pause now. Since the distribution of individuals' items, in this case wedding dress cost, is normal to begin with, or at least we're assuming it is, then the sample means is normal regardless of the sample size. And the mean of the distribution of sample means is the same as the mean of the individuals, which is $1,032. And the standard deviation of the sample means, also known as the standard error of the mean, is the standard deviation of the individuals divided by the square root of the sample size. So that's 550 over square root of 20, which is $122.98. So what's the probability that the mean cost of the wedding gown is between $800 and $1,200? Well, we can find that probability from a normal CDF because we're assuming this is distribution of sample means is normal, or at least approximately so. Well, exactly normal if the original distribution is normal. So it's normal CDF 800, 1200, okay, with a mean of 1032 and standard deviation S, which was found by 550 divided by square root of 20. Calculator gives us this value here, 0.8844 and so forth, so it's about 88.44%. All right, application 2. A manufacturing process produces circular discs. The diameter of the disc is normally distributed with mean 6 centimeters and standard deviation 0.003 centimeters. Product specifications for the disc call for the disc to have a mean within 0.01 centimeters of 6 centimeters. What percentage of discs are within product specifications? Work this out. Come back when you're ready. Press pause now. Well, this particular question doesn't have anything to do with sampling distributions. This is just the fact that we have a normal distribution here of individuals, and we can find a probability. Now, when we say the specifications call for it to be within 0.1 centimeter of 6. That means it's between 6 minus 0.01, which is 5.99, or 6 plus 0.01, which is 6.01. So if it's a good one within product specifications, if it falls somewhere between 5.99 and 6.01. Now, this is D is the diameter, and we're told that it's normal with a mean 6 and standard deviation 0.003. And so we work at this probability out with our normal CDF on the calculator. So that's normal CDF from 5.99 to 6.01 with a mean of 6 and a standard deviation of 0.003. This turns out to be 0.99914, etc., or about 99.91%. In other words, about 9 out of every 10,000 discs are out of specification. So we're talking about items per 10,000 at this point. A little less than 1 out of every 1,000. Now, for quality control, samples of 10 discs are periodically measured, and the mean diameter of the sample is recorded. Assuming that the discs are randomly selected, completely describe the distribution of sample means. Well, since the individual discs are normally distributed, the distribution of sample means is also normally distributed. So the sampling distribution will have the same mean, which is 6 centimeters, but will have a smaller standard deviation, also known as the standard error of the mean. So the standard deviation of the x bars, the standard error of the mean, is sigma sub x over square root of n. So it's the standard deviation of the population, which is 0.003 of individual items, divided by the square root of the sample size. 0.003 divided by square root of 10 is approximately 0.00094868833, whatever. Okay, so it's a pretty small number there. Graph the PDFs of the distribution of individual disk diameters and the distribution of sample mean diameters for samples of size 10. So graph both of these PDFs. Come back when you're ready, when you have this done. Use your calculator. Press pause now. Well, here's what the graphs look like on a TI-84. We're doing normal PDF of X with a mean of 6 and a standard deviation of 0.003. That's the individual distribution, which is the shorter, fatter one here. And then we do normal PDF X, still a mean of 6, but 0.003 divided by square root of 10 for the standard deviation for the distribution of sample means. And that's the taller, skinnier one. Notice that they're centered up at the same point. You have to try to find some sort of reasonable window. And I went, I went a little bit below a few standard deviations, probably about 3 or 4 standard deviations out of the mean of the individuals above and below this. It looks like I went 4 standard deviations. 4 times 0.003 is 0.012, so I went that much above and below this. So this is going out 4 standard deviations on the individuals. Of course, it's a lot more standard deviations than that, called the smaller standard deviation of the distribution here in the middle, which is the distribution of sample means. Here's a little bit better looking picture from a TI Inspire. So note that the distribution of sample means, the one in blue, has the same center, mean is 6, as the distribution of individual values, but it has a smaller standard deviation, which makes it more concentrated near the mean. So it's going to make it, in the middle here, it's going to make it taller and smaller on the outsides. In other words, less spread out than the individual items are here. What percentage of sample means fall between 5.999 and 6.001? What percentage of individual values are between those same two numbers? Press pause and work that out, please. Well, the percentage of the sample means that are between 5.999 and 6.001 is 70.8%. The percentage of individual values between the same two numbers are 26.1%. I found those with normal CDFs. So the first one was normal CDF from 5.999 to 6.001, mean of 6, standard deviation of 0.003 divided by the square root of 10. And that gave me, this number here, about 70.8%. For the individuals, I did the normal CDF, same lower, same upper, same mean, but the standard deviation is just the 0.003. Gives me a much smaller probability there. You can see this illustrated on this graph here. So the areas are shaded. So this red area is the 0.261, and that's the probability for the individuals being between those two numbers. The red plus this blue and all this blue up here, going all the way down, including the red there, and all the way up to the top of the tip top up here, all that area is 0.708, which is the probability that the mean, sample mean, will be within that range. So notice these are two very different probabilities, even though the two distributions have the same mean and they have we're talking about the same limits. The standard deviations puts much more area. The standard deviations being different and being smaller for the distribution of sample means puts much more area near the mean for that distribution of sample means. So in other words, we're much more likely to get an average of 10 items to be between here than we are to get an individual item between here. 90% of the time, the distribution of sample means will be between which numbers that are centered on the mean, and 90% of the time, the distribution of individual diameters will be between which numbers that are centered on the mean. See if you can figure this out. All right, well, the first thing to notice is if you're talking about 90% being in the middle, that leaves 10% on the two tails together. So that leaves 5% in each tail. So the left tail is 5%, the right tail is 5%, so that it leaves 95% below the upper boundary and 5% below the lower boundary. So if I do inverse norm of 0.05, the mean of 6, standard deviation is 0.003 divided by square root of 10, that gives me my lower boundary of 5.9984, and if I do an inverse norm for 0.95, mean of 6, standard deviation of 0.003 divided by square root of 10, that gives me 6.0016, which is my upper boundary. If I do the same thing over here but change the standard deviation back to just 0.003 for the individuals, I get the corresponding limits there. So basically, you know, this region right here for averages basically corresponds to this region right here for individuals. Of course, that's notice it's a bit narrower for this one here. So that is a narrower interval for the distribution of sample means than it is for the distribution of individuals to get the same area. So we saw earlier that 99.91% of the time the individual disks are within product specifications. What cutoff should we set on the distribution of sample means to make sure that 99.91% of the time they are between the cutoff values? See if you can figure this one out. Press pause, come back. Well, here's what we do. 1 minus 0.991 is 0.3 zeros and a 9, which is what this is. 9 times 10 to the negative fourth. So that's this, the 0.99, 3 nines and a 1. That is the probability that we're within, in the middle. So the two tails are going to add up to 0.0000, 3 zeros and a 9. Divide that by 2 to get how much is in each tail, and that's 0.00045. Add that to 0.991, and we get 0.99955. Now, what this says is this 0.00045 is the probability to the left of the left boundary we want, and the 0.99955 is the probability to the left of the right boundary. So that's what we're going to put in for our inverse norm. We're going to put in this number here, which is 0.00045. Give it the mean and the standard deviation of the distribution we're looking at, which is for the x bars, and then the 0.999556, and then this, and we get 6.003. Now, if we were to do this same thing and just put in the 0.003 here instead of the 0.003 divided by square root of 10, these should turn out to be our product specifications. But here are the corresponding values for the sample means. So if we get a sample mean outside that interval, we're probably getting some individual values that are outside our product specifications. All right, how about another application? The baggage weights for passengers using a particular airline are normally distributed with a mean of 20 pounds and a standard deviation of 4 pounds. If the limit on the total luggage weight is 2,125 pounds, what is the probability that the limit will be exceeded for 100 passengers? See if you can work that out. Think about that a few minutes. Press pause, come back when you're done. Well, let's see. Note that the mean weight of the sample of 100 passengers' luggage is normally distributed with mean 20 pounds and standard deviation 0.4 pounds. If the total luggage weight is 2,125, then the mean weight is 21.25 pounds. So we want to compute the probability that the normal random variable with a mean of 20 and standard deviation of 0.4 is above the 21.25. Okay, so let's think about this first statement here. Why is this true? Well, if each one is normally distributed with the mean of 20 pounds, then the average of 100 passengers' luggage weight is still 20 pounds, the same as the distribution there. Now, why do we come up with this for the standard deviation? Well, the standard deviation here is 4 pounds for the individuals. We have to divide by the square root of the sample size to get the standard deviation of the X bar values. Okay, so our sample size is 100. The square root of 100 is 10. 4 divided by 10 is 0.4. So that's how we came up with that. If the total luggage weight is 21.25, then the mean weight is that divided by 100, which is 21.25. So what we want to compute then is a probability that a normal random variable with mean 20 and standard deviation 0.4 is above 21.25. Well, that's a normal CDF from 21.25 up to infinity. Well, instead of infinity, we use mean plus 10 times the standard deviation. The standard deviation we're using here is 0.4, and the mean is 20, so it's 20 plus 10 times 0.4 is 24. So we can use that for instead of infinity here, or you could use something a little bit bigger than that if you'd rather. But so 21.25 to 24, mean of 20, standard deviation 0.4. Here this is, don't forget the e negative 4, which means times 10 to the negative 4, which means we need to move this decimal place 4 places to the left. Crosses over there, it's the 8 once, and then there's the crossover 3 zeros, puts it right here to be 0.000889. So that's pretty small. So it's extremely unlikely that they're going to be overweight, assuming the statements they make here are true. All right. All right, let's look at this application here. A trucking firm delivers appliances for a large retailer. The crated appliances have a mean weight of 300 pounds and a standard deviation of 50 pounds. Assume that these weights are distributed normally. A truck belonging to the firm has a carrying capacity of 8,000 pounds. What's the probability that it will be able to carry an entire order of 25 randomly selected appliances? See if you can figure that one out on your own and come back. Well, note that the mean weight of a sample of 25 crated appliances, which are randomly selected, is normally distributed with the mean of 300 pounds. And what would the standard deviation be? Let's see. The standard deviation of individuals is 50 pounds. We're doing a sample of 25, so we're doing 50 divided by the square root of 25, which is 10, and that's going to be the standard deviation of the sample means, also known as the standard error of the mean. The total weight of the lot is 8,000, then the mean is 8,000 divided by 25, which is 320. So what we want to do is to see if we're going to be able to carry it. It's got to be that 8,000 or less, which means on average it has to be 320 pounds or less per item. So what we want to compute is a normal probability that a normal random variable with mean 300 and standard deviation 10 is below 320. Well, that's done this way as a normal CDF. Well, instead of putting in negative infinity, we know the lowest weight is 0, so we're just going to put that in. So from 0 to 320, mean of 300, standard deviation of 10, That's 0.9772, etc. So about 97.7% of the time, that truck will be able to carry an entire order of 25 appliances. So most of the time, a few times not, but almost all the time, 97.7% of the time. Now, suppose the company is deciding to purchase a new truck, and let's say all the time they typically get orders of size 25, and they want to deliver them, and they want to be able to deliver these in one truckload at least 99% of the time. So what's the minimum size of a truck they need to get? In other words, what's the minimum carrying capacity? See if you can work that one out. Press pause. Well, this one is an inverse probability problem, so we're going to use the inverse norm. Now, as seen on the previous slide, the mean weight of a sample of 25 appliances is a normal random variable with mean 300 and standard deviation 10. So we're going to just do an inverse norm from that. So we want to find the probability that we have the amount of the answer or less to be 0.99. So that's an inverse norm, 0.99, 300, 10. That gives us 323.26, so forth, pounds per appliance on average. 99% of the time, that will be what we need to be able to carry. Well, we need 25 of those, so multiply by 25, and that's the total amount that we can carry. So that is about 80.81. We want to round up to 80.82. So about 8,082 pounds. Notice that these last two problems, application 3 and 4, both had something to do with a total amount, a sum, and rather than the average. But notice that if you have a fixed sample size, it's a real easy calculation to go from sum to average or average to sum. Okay, let's look at another example here. Manufacturers often use several collection of techniques called statistical process control, or SPC for short, to help monitor production and ensure quality. One such SPC technique is the production of what's called an X-bar chart. Such a chart is pictured here below. In this example, the dots here are going to be sample mean diameters of the product for samples of size 5 at different times, and they're connected by line segments. So the way this works is periodically, usually at pretty regular intervals, they pull off a sample of 5 items and measure them. They don't measure every single item, but they periodically measure them, and then they find the 5 diameters, write them down, add them up, divide by 5 to get a mean, and they plot that mean value here. So this one was about 55.5, and so forth. And they just plot those values, and then they connect them with this line graph. So we get this little broken line graph here. Now, we don't expect them to be exactly the same. There's going to be some variation there. Okay? Now, after doing this a long time, they can average those and get an average of where the process is, which is this red line, which is right at 54.1. And we assume that that's going to be the mean of the entire distribution. So that's basically our center, our mean. Now, the process is what they call in control when the distribution of sample means is approximated well by normal distribution. And there's some tests that you could, of course, do for that. Then they have methods of computing what are called control limits, and for this case, they are at 51.9 and 56.3, which is where these horizontal pink lines are down here at the bottom and the top. Those are called the control limits. Now, suppose the standard deviation of individual diameters, in this case, is 1.68. Okay? What percentage of X bar values will fall within the control limits? See if you can figure that out. Well, here's where I worked it out over here. I took the 1.68, which is the standard deviation of the individuals, divided by the square root of the sample size. Sample size is 5. And I got this 0.7513. Store that as S because that's the standard deviation of the sample means, the standard error of the mean. Now, I also put the 54.1, which is the mean of individuals, which is the mean of the sample means as well, and put that right here and store as M. So now what I'm wanting to do is to go from my lower control limit of 51.9 to my upper control limit of 56.3 with that M and that S for the mean and standard deviation, and I get 0.9967 or 99659, about 99.7%. So it's about 3 standard deviations above and below the mean, closer to negative 2.93 and 2.93. So those are the z-scores that go with these values, with the control limits. So notice that they're set approximately 3 standard deviations above and below the mean, and so that's about 99.7% of the data. So note that if the process is behaving normally as hypothesized, then 99.7% of the time it will be in there. So what happens if you're going along here and all of a sudden you get one that's falling outside the control limit? That would only happen less than, about 0.3% of the time. That would actually happen if the process was behaving like we thought it was. It's much more likely that what happened is the process has changed. Something broke on the machine. Something is done, an error, user error, a part broke, something's defective with the input materials. Something happened that was wrong. And so if a dot comes out here, then the person running the process is going to go, oh, wait a minute, something's wrong. Stop the process. Let's figure out, let's quit making all these bad items. Let's stop this and find out what the cause is and fix it. And so this is a pretty simple but very powerful tool out in the manufacturing sense. All right, and I believe that's going to bring us to the end of this video on some application problems with sampling distributions and the central limit theorem.